Okay, hi everybody. This is a bit strange, but doing this type of broadcast. But anyway, I'm really happy to be here, and thanks very much to inviting me to Sanjoy and his colleagues. And I'm going to talk to you for the next few minutes and take some questions. And I think what I'm going to do is tell you a little bit about who I am and what I do. My name is Lee Cronin. I'm based in Scotland, although I'm not Scottish, but my two boys are. And I'm based at the University of Glasgow, and I've been in Glasgow for almost 15 years, and I'm an inorganic chemist. And when I first joined the faculty at Glasgow, in fact when I was interviewed there, I actually told the interview committee one of the things I was deeply interested in that I was going to tell you about today, which is this idea of understanding the origin of life and also inorganic life. And I told this to my interview committee, and they all looked at me and shook their head and said, "Oh, not another one." And it turned out that I joined a faculty where a guy called Graham Cohn-Smith, who invented a theory about clays and the origin of life from self-replicating materials, and I'll tell you a bit about that in a minute. So I'm an inorganic chemist. That means I'm interested in doing chemistry on the elements that are not just carbon but fill the periodic table, so metals and salts, and understanding how they interact with each other. And I just so happen to have how they can form into really big structures. This is one of my favourite nanomolecules here. This is a metal oxide based on tungsten, which are these blue things here, in oxygen here. And although I can hold this in my hand, of course I can't really hold real molecules. This is about 1 billion times larger. It's about 1 nanometer in diameter. So I'm really interested in making nanomolecules. But it didn't start all there. I've always wanted to be a scientist, and I've always been interested in complexity, and I guess realised I wanted to do science from a very young age, from when I was probably a small boy, when I was about 9 or 10. But it wasn't always that easy, because there was a disconnect between how much I was interested in science and what the teachers thought I could do at school. And science has always been told, back then, I guess this is 35 years ago, or not as much as that, but that science was hard, and I was struggling at school. I was just so fascinated by the world around us, and also where things came from and why things got complicated. And this kind of shapes a lot of the questions that I'm thinking about in my science today. I mean, why did chemistry turn into biology is a big question. And can we do it now? Can it happen elsewhere? Can we do it in the lab? Can we do it on Mars, or Europa, and so on? And so I try to convince my teachers that actually I was interested in science and capable to do it, and I got through school and I got to university, and I realised I really enjoyed chemistry because I found it so utterly confusing. And so that's really how my fascination for doing things confusing started. I realised that science is about being confused most of the time, and I'm very good at that. But being confused with intent, I was not just being confused for no reason, but being intentionally confused is something I'm very good at. So when I started doing my research in Glasgow, I set out trying to make nanomolecules. And if you can see this molecule here, it has some symmetry. You might be able to see, like, if I could cut down the middle here, I could see this part and this part the same. So there's a really complex molecule here with lots of balls and sticks, and there's a couple of yellow things in the centre there that you may see. How do these assemble? How could I make this? And in fact, the way we make this molecule is by adding some salt together in some water and changing the acidity, and it spontaneously forms. So I get this for nothing. This is like an inorganic free lunch. I'm able to get a really complex molecule. And if you look at these two molecules here, can you see the difference between the two molecules I'm holding? There's something in the middle. You can see that on the one it's got a purple atom, and the other one has got two yellow atoms, and you can see that just by adding two different elements, which are not metals, they get them inside these rugby ball cages. I think soccer balls, you would say in the US. So I'm really interested in how do big molecules assemble. And when I started in Glasgow, I had to assemble a research group, a team, and the equipment to figure out how I could get the equipment to investigate this problem. But really I was hiding the problem I wanted to really look at, which is how did chemistry get complicated? Where does biology come from? And what is it about the periodic table and the laws of chemistry that are responsible for the emergence of life? And could we do it today? And so for the past 15 years, I've been working up to the moment where we can actually embark upon some real-time experiments in the laboratory, the aim to turn inorganic materials into biology. Not wait a billion years, not wait a million years, do it immediately. And some of the biggest ideas that we have is that the transformation from chemistry to biology is not impossibly difficult. It's actually very simple. And just like you see in technology today, I have my latest iPhone here. I don't know if you can see, it's very thin, and there's an iPhone, I don't even know what it is. Is it 6? Have we done 7 yet? This one is not the first generation, there's many that have come before, and this is obviously the most sophisticated. And I'm interested in how life started right at its simplest form and got more sophisticated in steps. And this is what I think seems to happen, is that life got more sophisticated in steps. And I want to understand how that happened, and there's some assumptions I want to challenge. And not knowing anything, and being paid now as a professor not to know anything, I can be really good at not knowing stuff. And so I can ask questions that other people probably wouldn't want to ask. So one example is, could life be very simple? Could it take just a few seconds? Probably not a few seconds, but could it take a few hours, a few days, outside a few years to start to spring in existence? And what would the first life forms look like? And that characterises a lot of the quest today. Not only are we trying to figure out those experiments to see what is it about the chemistry that we have on Earth that gives rise to biology. Could that happen anywhere? And what are we looking for? I mean, are we just going to make a mix of chemicals and try and convince ourselves a life form is coming out? That's obviously not correct. And the other thing is there's this entire field of science, origin of life, that have lots of very interesting theories about how life emerged, and we can discuss in the chat session. And do I think they're wrong? Well, I don't know. And what's an interesting way of saying, do I think they're wrong? It doesn't matter if they think they're wrong. I can't prove them. Not because they're a historical issue. The origin of life is a historical question, and therefore I prefer to frame the question in the present. If I could make a really simple life form in my lab and show how it could get more complicated over time, would that allow me to start to frame our existence in the universe? Wouldn't it be great if I could show that we could form inorganic life forms in my lab very simply? In a lab with other elements, we could instantly show that life was possible elsewhere. And a lot of interesting discussions, and certainly I'm not the only person with ideas, and many people with ideas, like people at JPL, like an old colleague from Glasgow, Mike Russell, who's thinking about how energy through matter organises in such a way that lifelike things come in. Obviously there's what groups are doing all around the world in trying to think about the geological consistency for what we might imagine was possible. So there's all these questions going on, but against the backdrop of how do we do an experiment? And one of the big struggles I had trying to assemble my research group at the beginning was, how do I get money to start to do origin of life, or more importantly, not origin of life, artificial life, new life work, because it's quite a difficult subject to get funding in the UK, and the technology we need is incredibly expensive. Some of the machinery that we need to buy to look at the molecular level are literally millions of dollars per piece of kit, and we need a lot of people to work together in teams to basically, you know, they're the chemists that are baking the cakes, if you like, and getting the ingredients right, and then there are people that are dissecting the cakes using modern spectroscopy to understand how that was put together. And so I had to really build my research group based upon the whole idea of making nanotechnology. So this molecule here actually is very good molecular flash RAM. We published this a few years ago, and the idea is that you can see this thing in the center. It's really, this purple atom here is really good at taking electrons, and so I can bombard this molecule with electrons, and this can hop up a bit, and that could store like a 1 or a 0, like a molecular braille, an indent. And so by doing this type of molecular nanotechnology and understanding how could I make molecular memory, I was able to start getting money that I could build an infrastructure to also ask these deeper questions. And it's also one thing I'd like to discuss with you. How is it that society and politicians accept that we can play physicists to look at the deep mysteries of the universe, but chemists aren't allowed to ask where we came from? How did that mucky chemistry become biology? Maybe we can, and maybe we just are not brave enough to ask that question. And one of the things I would love to do is be braver to ask these questions and engage people. And that's why I'm so delighted to be talking to you today, describing to some of the ideas that we've got going on in Glasgow, and also to show how probably there's a, I would say, young generation of physicists and philosophers and chemists and biologists that are all coming together that are actually sharing these questions. They're not unique to me. I think there's a global awakening. People are really think that they getting used to the idea that life is not that hard, or at least thinking if life isn't that hard, how obvious is it? So that's one of the things I wanted to say, a bit about me as an inorganic chemist coming to Glasgow in Scotland and looking for the origin of life. I've got to look for the meaning somewhere because it's very rainy up here. In fact, it's been raining in Scotland ever since I arrived in 2002, and it doesn't feel like it's stopped. So the other part of that is obviously asking a big question, also doing something that's technologically relevant. I want to tell you something else a little bit about what we do for 5 minutes, and then I'll maybe start to figure out answering some questions and how I can use the technology here to do that. And the other thing is, if we can understand evolution and how evolution got started, because evolution without chemistry or without biochemistry doesn't seem to make much sense. And so we're faced with this real conundrum where I don't want to invoke a creationist type argument for a magical appearance of a cellular machinery that can evolve, but we need to understand how evolution got started. And I think this is actually a really hard problem. But if we can understand the minimal machinery to make something evolve, can we start to think about evolving hard materials? And can we evolve new types of drugs, new antibiotics? Right now in the UK, I don't know if it's the same in the US or wherever you are, but the loss of antibiotics due to microbial resistance, i.e. overuse of our current drugs, so that the bacteria out-evolve and get round the current drugs, is a real problem. So one of the things I'm trying to say to people in the UK to actually explore this is, if we can understand inorganic evolution, or how we can make robotic platforms to do evolution outside of biology, maybe we can do that for drugs. And if we can do that for drugs, then we can start an arms race. We can go back to the Cold War, where basically we have the bacteria here, so that's the Soviets. Hopefully I'm not offended anyone. And the good guys here, that's the doctors. And then what would happen is that we'd kill some bacteria with the drugs, the bacteria would evolve, And then we find randomly another drug and the bacteria have out-evolved. But what happens when you keep going? Well, if we could evolve a drug, then it gets better, and then we do this. We can carry on the evolution almost forever to open up the pipeline of chemicals. So this idea that we would have orphan antibiotics would go away. So this is one reason why we should try and understand evolution. Why else should we understand evolution? Well, oh my gosh. I don't want to offend anyone's religious views, because religion and science for me don't intersect directly. They can respect one another. But I do not like using pseudo-scientific justifications to kind of validate a certain area. And evolution, and how evolution got started minimally, naturally, is obviously a very important quest. And we will do it. You know, I don't see the need for a high information content object that becomes magically invoked or creationistically invoked. Minimal evolution can occur. We just have to understand the minimum infrastructure to get there. And one of the things we can talk about is how, in fact, in my lab, we've been building robots to cheat and do evolution robotically. And so the robot is a bit like a molecular nursemaid. It feeds the chemistry, some molecules to keep it alive. It decides which molecules die, kills them, removes them, and then takes the ones it likes and makes another generation. So what this robot does is it evolves the chemistry. And by making robots and chemistry evolve together, what we can do is understand the minimal needs we have, the support mechanism to make chemistry evolve. And that's one of the other big targets, and that's really cool because we've actually been able to evolve all sorts of formulations. In the UK, formulation industry, making mayonnaise, shampoo. I'm using wonderful shampoo that my wife buys and I steal because my hair's got longer. But shampoo and soap and paints and all these complex materials can't be designed properly. They're better evolved. And we've been using robots to evolve salad dressing. And you can find some really cool videos online associated with my website where you can see these droplets going. And I think that that's really interesting idea to try and figure out how we can look at evolution using robots. Now, the other thing that we're trying to do in my team, and I find really, really exciting and really hard work, is convincing people who are really smart, and I'm really blessed in that we have a really smart research team, to basically ask questions that they have no idea what the answer is. Of course, all scientists, we want to explore some days. Sometimes we want to do experiments that just confirm our ideas. Some days we need that. Some days we'll allow ourselves to do experiments where we will allow ourselves to actually interpret the outcome in a different way. And this is something that I often spend a lot doing. I like to do pretty crazy experiments for fun, to confuse my co-workers, to show them how stupid I can be in the smartest possible way. And let me give you one example. So a few years ago we took a 3D printer, which is a normal 3D printer that basically prints an object in plastic, and I decided I would print test tubes with the 3D printer. And that's actually quite silly because the plastic would melt when you had acid and heat it up and it would just burn. But what happens if you print a test tube with a 3D printer and then you use a 3D printer like a cocktail maker, like a robot, to do chemistry in the test tube? And that's how one of the reasons we've started to combine digital science, robotic evolution and chemistry together. And it's kind of also confirmed this kind of wish. Ever since a young boy, I've been really interested in minimality and complexity. And what do I mean by minimality? Well, I travel a lot and I want to have maximum function in the minimum small case. So when I get on the airplane, I don't have check-in baggage, just hand baggage. So I want maximum underwear, computers, clothes, whatever I need. How can I get that in minimum space? So maximum function in minimum space. And since I was a child, when I used to make pocket survival kits, I wondered how I could use a given object for many different roles, you know. And this is the thing that I'm kind of playing with in chemistry now. It's like, how can we use the concepts of minimality to then get differentiation to show how we can start to build life forms or lifelike things. And it may seem a bit confusing, but just to give you a kind of, I'm always interested in, it's a bit like writing a really big complex program and you look at redundancies in the code and you remove bits because you don't need them anymore. A bit like that, you know, optimize the way you would walk to work during the day or drive there, rather than taking a long route, take shorter and shorter routes, so you have to do less and less things to get the same outcome. And so that is a really important concept, is to look at minimality. So I guess I've come from this idea of minimality. I became a chemist because at school I was told I was too dumb to do anything else, and I was confused by chemistry. But there's no shame in being confused by chemistry, because who isn't confused by chemistry? Well, maybe there's some chemists watching that aren't that confused, but I am confused about chemistry most of the time. And then when I became an academic and I realised that being confused is really a good way to do science, because you ask lots of interesting questions. When I moved to Glasgow and I realised that I could do nanoscience, I used the tools I assembled for nanoscience to start going back and say, well, why is chemistry special? What is it about inorganic chemistry that makes it different to organic chemistry? And to poke fun at organic chemists, because organic chemistry is the chemistry of life, of drugs, of biology. Could we make life using inorganic molecules? What stops us from doing that? Now, I think I've been talking for about 20 minutes, and what I think I'm going to want to do is start to hand over for some questions. And I'm not sure how this works. Now, I think this happens via the chat room, so I'm hoping Sandra is going to help me here, if you can hear me and so on, so we can get some questions. Obviously, I'm older than I am the technology. Right, so Rick was saying that you've been to get some system plan. Yeah, okay. So test the TAN where we could desiccate and see what chemistry is involved. So project gets some type of assessment employ on a life form returned from space on my website. Wow. That's a very interesting question. Is how can you yeah, okay, all right. There's a lot of ideas about this, like, you know, when you find kind of life-like objects, how can you figure out whether they're alive or not? And this is actually not a trivial problem. And I'm certainly not the first person to suggest or make some inorganic life form and determine that it's alive or dead. It's actually very tricky. And I've been having a lot of conversations with and perhaps one of the people who I think I'm beginning to understand, and she's beginning to understand me, and that's Sarah Walker. And I've been inspired by a lot of her work, because basically she's been able to describe life in a more abstract way. Because the problem with just bringing in some chemistry, it could be alive, it could be dead, but how can you figure out if it has in a TAN state, if it has no metabolism and it's actually dead? How can you account for that? Is it really a life form? So that's one important point we'll come to. One question is, how are you creating life in a test tube? And that's a very important question. And what we are trying to do is basically take a load of, let me go back a step and I'll go around all these questions, because now I can see the text you're throwing, so you can start throwing things at me. So before life on Earth, you had a dead planet. It looked like Mars, or, well, it didn't look like Mars, but it was featureless, like, I suppose, I'm not a very good geochemist. There was no living stuff, so there was obviously lots of activity, lots of chemistry, lots of sulfur, lots of iron and other stuff going on, but ostensibly there was no organic carbon. So what we wanted to do is just say, well, okay, let's start with a sterile test tube. What could we do to start a life form? And so what you want to do is start to put complex mixtures of chemistry together, simple chemicals, and observe the emergence of complexity. And this is one of the reasons why I started talking to Sarah Walker and her colleagues and people at NASA to say, hey guys, how do you guys look for complexity? And it comes back to what Rick was asking. And how do you start searching for that life form? So what we're doing in the lab is we're basically taking a guess. We're putting very small molecules together, very simple molecules, and we're adding energy, and then we're adding more material, and then we're watching how they develop and grow in time. But that's not enough. That's certainly not a life form. That is just chemistry. So one of the things we've found is that the chemistry can get to a certain threshold of complexity where it comes back down again. This goes to this metabolism and things that look interesting and reform. How can I look at something how can I judge how complex something is? So let me take this cup which has some tea in it. This looks like, if you found this, you know, outside, you go, oh, that's a nice cup, someone's patented it. Look, clearly this is actually what brought one of my Chinese PhD students years ago. It's a beautiful cup, you can see all the features there. It looks to me and you that someone has drawn a picture. But if you weren't able to interpret that picture, how would you know that was a picture? And so it goes back to almost some kind of arbitrary distinction between what collection of objects together is just so improbable that it had to be put there by a machine. And so what colleagues in physics and biology are teaching me is I need to work out how to do chemistry that makes me a really small molecular machine. And it goes, how can I find that? And what does that molecular machine do? It will have a certain number of features. It will make more of itself, and it will get more complicated over time. And I think that is not the answer, but it's the beginning of a way of coming up with experiments that we can benchmark. So I want to be able to start with something that's really simple in my test tube and wait some time, give it some raw material and some energy, and I want to go more complicated, more complicated, more complicated. And if you're not convinced, go back to your iPhone and think, and I want you to do a thought experiment. Imagine, we're in this thought experiment, think about where all the silicon chips in this iPhone were made. Now, imagine those factories did not exist. And somehow they were removed from existence. What would you need to go through to replace the silicon chip factories? And basically computers make computers. So I'm guessing what I'm saying, what simple computer made of valves and levers and all sorts of other governors would be required to make a more complicated computer that could make a more complicated computer so I could get back to this. And this is the staircase that leads to biology. And so you need to have some kind of metric that allows you to look for complexity. So another question, someone just asked if I have a publications page. That's a very good question. If you go to www.croninlab.com, there's a publications page there. If you click on the publications page, if you click on the P, you can get linked to some of the direct downloads. And also there are some open access papers there. If you want authorization to download, just email me and I can give you reprints. So Nicholas asks, how do I account for probabilities when considering your own origin of life experiments? I got this spontaneously to work or close to spontaneous work from a seed or life, and that's the big picture. What's the picture in the lab? Well, that's a really important question. Probability is a really important point, and it's really even harder than that because chemists cheat. They take pure chemicals from the shelf and they mix the pure chemicals together and they make molecules. And they say, oh, because I use chemicals that are present on early Earth, this is what we call prebiotically plausible. And so that is really quite tough. Just checking you're all still there. And so that's a really important question about probability, about how you would do it. And I think that the way you do it is, again, you have to work out about this metric for complexity. And again, I'm aiming in the chemical sense, and then I'll go and move to the next question. I want to make a molecule that's so complicated without any inputs, without any external cheating, that it would be equivalent to you going to Mars and saying, and finding this iPhone and it worked. And you either deduce that Apple's gone galactic or another life form put it there. And so I think that's really important about how we define complex, and I'll come to what Richard has just said in a second. And in terms of what I said about chemists cheating, they take pure molecules that they get from the catalogue and put them together and cheat. And it's a bit like making a cake. If I give you the ingredients to make a cake, you can make the cake in a billion different ways. But if you don't have those pure ingredients, you're even in a harder state, and that's where chemistry is. When it comes from, so Sandra just asked a question about teachers discouraging me from pursuing science. Well, yeah, they did. I mean, I don't really want to go into my learning difficulty childhood thing because it's not that it's boring. It's obviously very personal to me and might also be interesting to some of you. I think that what I want to just say is I found learning at school really hard because no one was interested in my interests. I was always interested in other stuff. Now, and I think my teachers thought, and maybe I was pretending to be too smart, you know, that I was bored by the monotony of the day, you know, so I just talked about other stuff I had no idea about, and teachers used to think I was making it up. That's why they discouraged me, because literally, you want to be a scientist, but you can't read or write. And my reading was fine actually. I just chose not to read the books, and my writing was pretty scrawly. It still is, and the way I got around it was I was just deeply interested, and that interest didn't go away. And my advice to you, if you are being discouraged by someone you really want to do and you're really passionate about it, just keep asking the question. Because in the end, if you aren't giving up, the number one thing you can do if you want to be a scientist is not give up. And I think that's really, really important. Science is about criticism, rejection, confusion. Science is not, you know, the glamour of knowing; it's the glamour of not knowing, if you like. And if you like that, and in fact, the question is more important than the answer. And as long as you're using a good framework to get to that answer. Now, Richard just asked a question, Richard Gordon, about meteoric. I can't say the word. Organic matter from meteorites is regarded as more complex than what we need for protocells. So the origin of life would involve a decrease in complexity. Well, we need to tell the difference between a mess and a complicated molecule. So meteorites have lots of organic polymers on there, and they look complex, but they're not. They're just messy. Okay? And so, Richard, I think, and this is really interesting, and this is one of the things that we have found, that meteorites actually don't have molecules that are that complex. They have decomposition products that are randomly messy, but there is a difference between complex and messy that we can go into. And I'm still arguing with colleagues about this because Murchison is extremely interesting. The molecules found in it and the polymers are extremely interesting. But what I mean is if you can find me a large amount of a complex molecule on a meteorite that has a molecular weight greater than a certain amount, I'd be really excited. And so actually I disagree. I think that we haven't yet found evidence of complexity anywhere else on Earth. And that brings it very nicely to the question about, you know, is there life elsewhere in the solar system? I think there is. And I think actually that's probably why we need to go to the rest of the solar system, have a look. There's definitely life on Mars, and I'm saying, oh yeah, of course he says that. Well, we put some there because in the probes, we sent a load of stuff there. And I think actually there is life on Mars, and it's probably almost Earth-like. And probably we are Martians, and the reason for that is it just increases the search space. And so it's a bit like Mars started earlier, it was more habitable earlier, chemistry was going on, so chemistry on Mars was getting complicated. And let's say chemistry on Mars was getting complicated but not quite lifelike. Earth was it was a bit complicated, bit messy, everything was being erased. And maybe there was I don't know this because I know no history of that at all, is that there was some of that complex chemistry, not life, complex chemistry that had built up over time, got ejected from Mars, made it to Earth, and suddenly found an abundant set of building blocks where it could carry on getting complicated until it could reproduce itself, and it could basically it could start to act on itself. And I think the difference between life and non-life is sufficient complexity to own your to basically determine your movement in the environment. So basically it's intention. I know it sounds a bit wishy-washy. So there's life on Mars probably, and it's probably Earth-like. And that does that mean that we are Martians or it came from Earth? I don't know. You might not be able to tell the difference. What would be incredibly exciting is if we found life on Mars and the amino acids were different, slightly. The genetics were slightly different. We could find a different Luca. That would be cool. Well, I mean, more than cool. I think it would be absolutely spectacular. But what I'm going to is I think there is life elsewhere, and I think Europa is a good option. In fact, I think anywhere where there's a difference in temperature and there's energy coming in and stuff going on, I think that there is the opportunity for life to form spontaneously. And I think that life is not incredibly improbable. I think life is actually just a feature of the universe. What I don't think, or I don't know, is what percentage of life forms become multicellular. And then what percentage of life forms become intelligent. I don't have any feeling for that, and I think we can look at the Drake equation and so on and think about that. And isn't it fascinating that when we solve the origin of life problem, then we've got the multicellularity issue, and then we've got the how can we make artificial life forms that can actually turn into intelligent ones. Rick's asked a question about do we anticipate using chirality and amino acid counts and unravelling the complex model as you seek the minimal life stuff? I think so. What is not clear to me is whether chirality is required for life or how chirality emerged from life fighting it out. It's a bit like Betamax and VHS. Wow, there's lots of questions coming now. Oh, hello, Cole. Yes, von Neumann also considered how he could make machines which could make machines. He then suggested that there was some critical threshold over which complexity these machines would increase and below which complexity would decrease. Well, yeah, but von Neumann was an engineer. And I would say, and I think you're right, this is a very smart question, too smart for me. But let me answer the question. I don't think there's a separation in complexity. I think it's gradual. But we might see a threshold somewhere. I don't know, I'd like to agree. Well, I don't know, Cole, do you think there's a threshold? By which, you can say, yeah, definitely dead and definitely alive. I'd love to do that in some undergraduate lectures, Some people look clearly dead, but they then, but I think it's a question of maybe our understanding of aliveness will change over time. Certainly I can tell you what definitely is alive, and I can tell you what definitely is dead in my view, and I think I might convince you to agree. Will it be arbitrary? I don't know. Until we make another life form or we discover another one, it's a bit like flight. That's why I love aeroplanes, or the whole concept of the aeroplane. Before we had heavier than air travel, so don't count balloons, we just had insects and birds and so on. So we get a notion of what flight is. It was basically an object that could do work, push down the atmosphere and go up in the air. But when we built the aeroplane, the glider, the rocket, we got more of a feeling of what is clearly flying and not flying. If I jump out of an aeroplane with a wingsuit, I can fly for a bit, I can glide. So there are distinctions there. There's another question. Do I see the possibility of finding organics inside Martian evaporite deposits such as, such as confirmed? Yeah, I think so. I don't know much about that, and I need to get much better at my meteoric chemistry and geochemistry. What I would like to do though, what I'd like to be brought is a meteorite in which had basically molecules like strychnine or morphine or methamphetamine, not because I'm some kind of extraterrestrial Heisenberg, Breaking Bad, but because those molecules are highly compressed examples of complexity. So what I have a theory, I'll tell you a theory that I guess is going to be, I want to be careful about not giving unpeer-reviewed theories, because unpeer-reviewed theories are nonsense, and well, they're not nonsense, but they're not peer-reviewed. So just because, and peer-review, oh well, we could talk about peer-review, but I think, so biology on Earth produces natural products. Those natural products like caffeine and morphine and strychnine, they are highly compressed molecules that have some interesting effects in biology. Caffeine, good old English tea. Caffeine and so on, and those natural products are really bizarre. They're highly compressed, they're highly detailed, they can't randomly form. So what I would love to see, and the thing that really would, like, I don't know, I think these are the type of things you live for, right, in science. Someone brought me a meteorite where I was able to identify an alien set of natural products, like natural products that look like caffeine that you just never seen on Earth before. Because let me tell you a number, let me tell you something. As a chemist, so I can show you a molecule here, you can see this molecule's quite big, lots of atoms. If I was to make every possible molecule that had a weight less than 500, so that's basically if carbon has a weight of 12 and we have protons and hydrogen atoms and so on, and nitrogen, which weighs, you know, you add them all together. If I was to make all the molecules that were possible by the laws of chemistry below just a molecular weight of 500, I would fill up 1.8 universes-ish, depending on how you do the counting, worth, close pack. Like, just imagine a universe where I had molecule next to molecule, and every molecule was different. How mind-blowing would that be? That there's so many more possible molecules. The ones we have on Earth are nothing compared to what's possible. So, on a Martian meteorite, we should find different natural products. And so, yeah, Richard has said that he thinks that multicellular, or he muses that multicellular organisms may be fairly simple, despite our belief they're complex. Well, no, I don't think it's about belief. It's about how we can measure complexity. And we're working on this right now, and I can't give too much away yet because we are trying to work out how to explain it. But Richard, I believe soon, within the next year, we'll be able to give you a really good metric for measuring complexity. Because right now, you're right, it's kind of arbitrary in terms of looking at this kind of morphogenesis, embryogenesis. But I think that's that assignment in that what we would call state space, number of possibilities, you're assigning a complex quality to that, or sorry, you're saying there's a simple quality to it and complex things are actually simple. And so when I think about complexity, I think very, very simply, how easy is it for me to make myself a phone? If I was to build this phone atom by atom, how easy is it to make it? And how many instructions do I have to write down? Then when I've written the instructions down, I can then compress it, let me compress it, zip it up, and how big is it? And that's where we get to complexity, is having a real feature. And again, the physicists, the Arizona group, there are people in Colombia, people around the world, we're all discussing at the moment how we can start to measure complexity, and it's really exciting. Do I get contacted by creationists or other scientific extremists about my work, and how do I deal with them? Yeah, not so much actually, and that makes me very happy. Not because I don't want to debate, it's just that, but probably one of the reasons why I don't get so much is I'm relatively respectful of religious people, because I know a lot of religious people, and I don't kind of, there are some people who I won't mention who kind of have intellectually look down on people who believe in something. And actually I think there's some misunderstanding. I mean, we all believe in something, and so I believe there are two ways of viewing the world, or not I think there are two ways of viewing the world. There's a belief framework and there's a science-based framework. They don't really intersect. They touch, maybe really small. So when a creationist tells me I'm wrong or tells me something, I just say, no, you have a belief that I can't test. And I'm not going to tell you you're stupid or it's incorrect. I'm just going to say that that's an interesting belief. But let's talk about the scientific framework. And so I don't think religious people would like me trying to smuggle science into their church. So why should we let creationists smuggle religion into our science lessons? Okay, put creationism into the religious education, but don't let the two occur. And I think that that's an important thing, and because I try to be as respectful as possible, I think that actually I get a little bit of respect back, and we don't have arguments, and I don't go, oh, you know, how dare you believe stuff, you're stupid. I just say, please don't try and pretend a belief is scientifically validated with a scientific method, because I don't think that's fair. If I'm going to respect your belief, please respect the scientific method, because on planet Earth we're facing lots and lots and lots of big challenges, and if we don't start to use evidence-based policy making, we're all going to die. And so I deal with creationists and other extremists with respect, and I have some really interesting conversations that I get quite confused by here and there, and so, you know, I'm always interested when someone tells me they have a crazy idea, because I get told by my colleagues in science that I'm completely crazy and some of the stuff we're doing is silly. And I try and challenge them on that and say, well, why? And I'm not, you know, I'm not a crazy creationist or a crazy anyone. I try to ask really challenging questions and then frame it scientifically. Yeah, so I think supplying data on embryos for complexity measure might be good, and you also need to think about complexity measures in general and how you cut things up and measure their absolute complexity, Richard, and that's a really good point. How can biology help us understand the origins? What do you think the most exciting biological experience addressing origins questions? How can they be improved? Wow. Well, one thing that I'm really interested in is how we can start to redesign minimal biology. So I like synthetic biology for that. How can we, you know, how can we get rid of all this evolutionary baggage? Because, you know, we as sentient beings can make assignments and remove things and make a simple as possible complex life form, so make it really compressed. So I think biology can maybe help us do that. But I think actually there could be a problem where there's a disconnect between biology today and the origins. Like, take the iPhone. Would you guess that there are other phones? I can't have a picture of like that old, you know, phone with a cable coming out of it and a horn and so on. I mean, there's nothing you can do here except to go back to that. I think I can get an old-fashioned ringtone up which will remind you of it. And I think actually some people overstudy biology, and this is where the RNA thing comes in. One of the things about the origin of life is there are like three kind of schemes. There's this idea that there's an RNA world. And the RNA world, because it's heavily involved in biology, or not, RNA is heavily involved in biology, and RNA is interesting and does other things according to some experiments. People think that RNA could have meaning for origins. And I have difficulty understanding that. Yeah, so one says we're looking at, let's not look at life as we know it, but life-like structures so complex they may not seem like life, and yet once we're in one they are. Kind of sounds like Gaia. No. Kind of sounds like Gaia. Yeah, okay, yes and no. This is a really smart point. The Earth is an ecosystem. An ecosystem requires living entities in it. So yes, it is kind of Gaia. Here's the thing, an astronaut in space is not alive. They can't reproduce. Not on a generational timescale. If the astronaut comes down from space and has a family or has further children, then it's generationally alive. It's metabolically alive. So the concept of aliveness isn't just about my metabolic state or the fact I have cells. It's my ability to go forward into the future. And so, since no one's asked, why is what you want to do different to Miller or Calvin or Oro or Fox in the chase for chemical evolution? Rick, you're too... you know what? Probably not that different. I just wonder if I have the book nearby. One of my favourite books, if I can find it on my bookshelf. It's gone away. It's hidden from view. It's actually Bob Shapiro's book. We have technology and we have ideas about... so we have robots, we have ideas about complexity, and we have great analytical methods. And Sidney Fox, for me, is just an unsung hero. And yeah, you know, one of the things I tell my research group, I have all these crazy ideas, and my colleagues out at the university say, you're crazy, and we're not going to give you money for this, and it's just stupid. And then the other half, people will talk to me and say, that's a really old idea. So I have half the world saying, you're completely crazy in science, and the other half of the people in science saying, you're not original. So some days in my life are quite amusing. So yeah, so there are some chemical origins. You know, one thing I would say about this as we come to the conclusions is no origin of life, no biology. No biologist, no biology, you know, no biologist. And in the end, no biology, no philosopher, no philosopher, no philosophy. And so there is this complex state that we go through about aliveness and complexity and looking for complex stuff. But there's looking for complex stuff that has module dependency, i.e. stuff that couldn't spontaneously arise. Let me just be clear, this mobile phone with some tweets on there, lots of tweets coming. This mobile phone has a 0 probability of spontaneously arising in the universe. 0. By chance. Do not let the physicists fool you and say, if you go on for long enough, if you have enough big enough universe, this could form. No, that's complete rubbish. There is a 0 probability that this will form on its own. If you find something complex enough, either it's a biosignature or it's alive. I would suggest to us, to you, to myself, to my group, let's go and make the most complex thing we can, naturally, or encourage it, and work out how we got there and ask, is it alive? Let's find the most complex thing we can in the solar system that's not come from Earth and ask, is it alive? And we will get closer to answering this question. And if I can make a life form in my lab that looks nothing like, or if I can make something that's complex enough in my lab that doesn't use DNA, but I use a robot, so I cheat, and you know, I use a robot to get it going, and it gets, off it goes, inorganic life. What does that tell us about life elsewhere in the universe? Well, it tells us that life doesn't have to be based on carbon, and that is a fascinating goal, and something I think we might actually do. It won't be as sophisticated as biology, because it won't have multicellularity and all this other stuff. It won't have had all this time to do evolution with our genetics, because we need that. But go look for complicated stuff, and I think that will change the way we see the world. It will change the way we view the history of planet Earth, and it will change the way we search for life in our own terrasphere. I think that Paul Davies actually is right. I mean, you know, some days I hate to say it, but no, I'm really inspired by his shadow biosphere idea, and I think I know how to go search for it unambiguously. And so that's really exciting. I think we will find alien life forms on Earth, and we'll find them quite simply, and we'll go, oh dear. You know, imagine 2 life forms on a planet that doesn't rotate, dark side, light side, and they, you know, life forms. Anyway, that never see each other, or never, evolve with each other. The only way they recognise each other is when they become intelligent. It wouldn't be interesting if there are other life forms on Earth we just haven't spotted yet. I guess there probably are. And we're just conditioned not to see them, or we ignore them. And what we need is a robust measure and start to have that aliveness scale. So we need that aliveness scale, definitely dead, definitely alive. Let's look at the middle. alive or dead, and then we start to classify them, go from there. And we have to collaborate together to do that. So I'm excited about the collaborations I've got. I'm certainly excited about the way organisations like SaganNet are putting things together and getting us all talking and discussing and doing outreach, because inspiring people to think about questions in science and also inspiring people to ask those odd questions is the way that we are going to shift things forward. Dogma needs to die. So, you know, I like to kill dogma. I don't want to be killed by the dogma, but let's see. So how much more time? Are we finishing now? I'm happy to stay online for a couple of minutes more, or are we now done? I think we might be done. Oh, Twitter's talking to me. Yeah, I think it's really important that we challenge our dogmas. And that's one of the reasons why I quite like this. I mean, it's a very, like I say, half the world tells me I'm crazy, and the other half of the world tells me it's not original. And so maybe we are just unoriginal and just crazy, which would be really bad. But I take that as a positive, because I think we are asking a challenging question about complexity, and we have to, and all the questions, I mean, I'm really pleased with a lot of the questions because they're really important. There's no magic way to identify complex forms that we can't count, and it all goes back to this measurement of complexity and various approaches that scientists have taken. But I believe we have a new approach to it, and I'm really excited about that, and I'm looking forward to sharing that with you in the future. I'll be happy to take questions offline if you want to email me. I'm very happy to continue the conversation, come back again. Thanks again to the people who run this site, and Blue Marble Space and NASA, Astrobiology and Elsie and so on, and to Sanjoy and Sarah, and to all of you who've been listening. And I hope I don't sound like a blubbering moron, and hopefully you're interested by some of the things I have to say. We're certainly really excited. Final thing before we finish is I want to thank not only you for watching, but also my research group for helping drive a lot of these ideas. They are consistently putting up with me and re-educating me and challenging me in ways that I just didn't think possible. And also, I should thank people who give me money, because we've got a lot of privilege to do this. We need more money, of course, so you know, if you know any rich people that want to really answer the question, then you know, direct them in this direction. And yeah, I think it's really interesting. Please be inspired by this. Please think about it. Why are we here? What is it about chemistry that gives rise to biology? And I think it's going to be more obvious than we think. Is that going to be disappointing, or is that going to be comforting? I'll let you decide the answer. Okay, bye guys.